Good morning, everybody, and welcome back. Today is Tuesday, and we're right in the middle of our gas chem unit. So you guys should be getting pretty good at doing those calculations using the combined gas law, which is both Boyle's and Charles' law, all in one really handy formula for you to use. The tricky part is rearranging and solving for the unknown, canceling out units. Today we're going to be doing Avogadros Law, and this one has a little bit of theory on the front end, so I'll be sort of explaining and giving examples for about 5 minutes. And then it is simple math, just like we were using already. So solving for units, canceling out, and figuring out your unknown. So that's where we're headed for today, okay? And I'm going to start off with, on your data sheet, your periodic table on the back, you have those STP, SATP. We're going to be using those numbers today with Avogadros Law. So let's just jump down here right now and talk about Avogadros Law. So it says that equal volumes of gases, it doesn't matter what gas, any gas, if they are at the same temperature and the same pressure, they will contain, and this is the important part, equal amounts of molecules. So what does that mean? What does that look like in terms of math? So it means that if we take a gas at STP, remember STP is 0 degrees Celsius in 1 atmosphere. It doesn't matter what gas it is, they all occupy 22.4 liters. So it is written as 22.4 liters per mole for any gas. So it's called the molar volume at STP. And it doesn't matter if it's hydrogen or helium or neon or oxygen or carbon dioxide or SO2. They all occupy 22.4 liters. It's a weird idea because they all have different molar masses, right? Like hydrogen is 2.02 grams per mole, nitrogen is 28, carbon dioxide is 44.01. So even though they all have different molar masses, they all take up the same space when they're at the same temperature and the same pressure. So that number you don't have to memorize, it's on your data sheet. Okay, that's important. You're going to use it a bunch. And I'm just looking at mine. So they give you the number, but they do not give you the units. Oh, they do. Very bottom right-hand corner. Volume at STP is 22.4 liters per mole. Now at SATP, so remember this is a little bit warmer, 25 degrees Celsius, and the pressure is almost the same. It's 1 kilopascal lower, but this is the biggest difference, is that it's warmer. So if you think about it, what's going to happen to a gas when you heat it up? It's going to expand. So what is the molar volume in a warmer gas? 24.8 liters per mole. And again, it doesn't matter what gas it is. All gases at STP occupy 24.8 liters per mole. So that's molar volume number 2. 24.8 liters per mole. And notice when I write the units, it's always liters on top beside the number, 24.8 liters. And if you forget, it's on your data sheet. Blue is not a very good color. And it is written as volume at SATP on your data sheet, 24.8 liters per mole. So these are the numbers that our whole lesson is going to be based on today. Now, we are going to do a little thinking exercise here. So I've got 2 balloons. This one contains 1 mole of oxygen. And this one contains 1 mole of hydrogen. So according to Avogadros Law, let's say that they are both at STP. Both balloons are at STP. What would be the volume of the oxygen balloon at STP? 22.4 liters per mole. Okay, what about hydrogen? Same. Volume at STP, 22.4 liters per mole. So if each of those balloons has 1 mole of gas, then they'll both have the same volume. Now here's the thinking question for you. I'm not sure if that's right, so we'll just cover it over. Why did black not show up? There we go. Okay. So oxygen has a molar mass of 32 grams per mole, and hydrogen has a molar mass of 2.02 grams per mole. Which balloon is heavier? Well, just using common sense, if this one weighs 32 grams for a mole and this one's 2.02, of course the oxygen is heavier. And you can figure it out. If we have 1 mole and its molar mass is 32 grams per mole, the moles cancel out and we would get 32 grams. So this balloon, 1 mole of it weighs 32 grams. And this one, if you did the math at 2.02 grams per mole, you get 2.02 grams. That's lighter than air. So it floats in air. And oxygen is not lighter than air, so it will not float. It will sink. How can these two balloons have the same volume? Well, that's Avogadros Law. Doesn't matter what the mass is, the same moles take up the same space. Space or volume. If you're having a hard time getting your head around that, the idea is that the molecules are so small compared to the space they occupy that their mass doesn't affect their space they occupy or the density of the individual atoms. Okay, so now we get into the math part. Get your calculator out, and if you've printed off your notes, you're going to follow along and solve these in the space on your notes. If not, you can do them on a separate sheet of paper. Okay, so determine the volume. So we are looking for the volume of nitrogen gas. So volume of N2 gas. Okay, we're solving every one of these by units. So we're looking for the volume in liters. Now they're telling us it's at STP, so you have to remember that SATP, that means for every gas, it's 24.8 liters per mole. So you should write that down right beside SATP because that's what it's telling us. Use that conversion ratio. All right, so now we are looking for volume. The unit we're looking for is liters. And there it is. That's the unit we're looking for. So when you write the question, you always put the unit you're looking for on top so it's in the right spot. So to solve for liters, all I need to do is cancel out the moles. And there's my moles to cancel out. Do I put it on top or bottom if I want to cancel out with this moles? Correct, on top. 1.25 moles, a mole divided by a mole cancels out, and we are left with liters. 24.8 times 1.25 is 31.000 liters. 3 sig digs, 3 sig digs, 3 sig digs. 31.0 liters. Okay, that's the math. So hopefully you're finding that pretty straightforward. Emily, got it? Good. Okay, all right, let's move on. I know that Marissa is chomping at the bit to dig into some more examples. All right, predict the moles of oxygen gas. N means number of moles of O2 gas. So that's what we're looking for. We are combusting 5 liters of butane at STP. Okay. So let's ignore the combustion part of this and let's just think if we had 5 liters of oxygen gas. Let's just change this. Predict the moles of oxygen gas required if we had 5 liters of oxygen. That's a better question at STP. Okay. So moles of oxygen if we have 5 liters of oxygen. Okay. So it's STP. That means we should write down 22.4 liters per mole. That's what that means. Okay, we're looking for moles. So here it is. That's what we want, but it's on the bottom. So we need to flip it. Okay, we have to have the unit we're looking for on top. So Blake, hopefully that makes sense to you. So we're going to flip it, Josh. Moles on top, 22.4 liters on the bottom. Okay, so I've got my moles. That's what I'm looking for. I just have to get rid of liters. There's how I'll cancel it out, 5 liters. 5.0 liters. Liters on top and bottom cancel out. 5 divided by 22.4 is 0.223, repeating, moles. Sig digs, 2 sig digs, and 3. So my final answer is 2. 0.22 moles, number of moles of oxygen gas. Okay, hopefully you're finding this pretty easy so far. And now we'll move on to the next one. We've only got a few left to do. Nice short lesson today. Okay, so our next guy. Richard, you ready to roll? Brendan Miller. Okay, so here we go. Determine the mass of helium at STP that has a volume of 10 liters. Mass of helium gas at STP, 22.4 liters per mole. Okay, so we're looking for the mass of helium. That means grams. Okay, we've got liters per mole, and I've got liters. If I multiply those, I get moles, but I need mass in grams. How on earth am I going to get the mass in grams of helium when all I have is moles? Hopefully some of you right now, Joe, are thinking, oh, right, I need molar mass. So capital M means molar mass. The molar mass of helium is 4.00 grams per mole from your data, from your periodic table. Okay, so this is going to be useful because there's my grams. So that's where I start. Always put the unit you're looking for in the front on top, 4.00 grams per mole. Molar mass of helium. Now I just need to cancel out the moles. And there it is. So I need to flip this one. Flip it, moles on top, so that those cancel out. 22.4 liters on the bottom. Okay, I've got my grams, but I need to get rid of that liters. And there it is, 10 liters. 10.0 liters. And now I can cancel out the liters. And I get grams. Perfect. That's what we're looking for. So now the math is 4 times 10, which is 40, divided by 22.4. So 40 divided by 22.4 is 1.7857 grams. I go back to my question, and I've got 3 sig digs, 3 sig digs, and 3 sig digs. So I need 3. So that will round up to 1.79 grams, the mass of helium gas. That's about as hard as they get. So if you're feeling pretty good about this, you're thinking I got it, then you can try this last one on your own. So pause the video here, try it on your own, and then come back and see how you did. Answer's right there, but I'll show you the solution. All right. Determine the volume of CO2. Oh, shoot. Oh, well, let's do that. Volume of CO2. Okay, so it's at STP, 22.4 liters per mole. We've got the mass. So we have grams, we have moles, we have liters. So I need to cancel out the grams, the moles and the grams. How would I find something that can cancel the moles and the grams for CO2? Molar mass of CO2. 1 carbon, 2 oxygen. The molar mass is 44.01 grams per mole. So there's our units we'll need to cancel. Okay, so we're looking for volume of CO2. So we write volume on top. 22.4 liters per mole. Okay, here's our moles to cancel out with this moles. So I need to flip this one. Moles on top. 44.01 grams on the bottom. Moles cancel out. Okay, and the last one is grams, 35.0 grams. And I'm putting that on top so that those grams cancel out. All the units cancel out, and we're left with liters, which is what we're looking for. So we'll multiply those together, and you get 17.815 4 liters. Sig digs on this are 3, 4, 3. So my final answer is 3. Volume of CO2. Okay, last one, and then we're going to do a little video to finish up. So I'd like everybody to pause and try this one on your own. See if you can get the 7.15 grams of chlorine, and then come back and check my work to make sure we agree on sig digs. Okay, mass of chlorine gas. Okay, so we are going to need grams. And hopefully you figured out by now that we'll need the molar mass of chlorine. It's diatomic, Cl2. So it's molar mass times 2 for chlorine atoms. So that becomes 70.90 grams per mole. Okay, we're looking for mass. So I'm going to write 70.90 grams per mole. There's my mass right there. We just have to get rid of moles. How do we get rid of moles? Oh, SATP has moles in it. 24.8 liters per mole. Now, sometimes what students will do is they'll flip something, but they won't flip the number. So for example, they'll write this in and they'll put moles on top and they'll put the 24.8 up there. But you can't do that. The 24.8 belongs with the liters. I'm just going to erase this and redo it. So you can't, if you're flipping a unit, you have to flip the number and the unit together. So this whole thing gets flipped. Moles go on top, the 24.8 and the liters on the bottom. Okay, so those cancel out. And now we have grams per liter. We have to get rid of liters, and there it is. 2,500 milliliters. There is 1 liter has 1,000 milliliters. So that becomes 2.500 liters. It still has 4 sig digs. And I'm putting it on top so that the liters cancel out. Plug it into your calculator and you will get 7.147 grams, 3 sig digs, 3, 4, 4. So that rounds to 7.15 grams. Happy days are here again. Okay, that is it. Now, before I give you your assignment, I did find this awesome little video on Avogadro. Sings a little bit about Avogadros Law and how it works. So enjoy. Be like 1 minute.
Amadeo Avogadro lived in Italy, and his work means an awful lot to chemistry. Amadeo Avogadro may be dead, but we all should remember what he said. Equal volumes of gases at the same temperature, pressure, have the same number of molecules. Amadeo Avogadro, that's his hypothesis. You got 2 balloons filled with different gases, equal volumes, but they both have different masses. If conditions are the same everywhere, tell me, how do the number of molecules compare? Equal volumes of gases at the same temperature, pressure, have the same number of molecules. Amadeo Avogadro, that's his hypothesis.
Well, isn't that a lovely song to have stuck in your head for the rest of the day? I put the link on that in my lesson so you can go to YouTube and watch the entire thing as many times as you would like. Okay, today, this is not right. So study guide, there's like 4 questions to do in your study guide on page 164. I'll put the answer key online for that. Textbook questions, the answers are on page 783 in your textbook. And I am going to give you a little practice quiz on combined gas law and Avogadro's law, and that's going to happen on Wednesday. So it'll be just like a little 5-10 minute, and I don't think Yeah, I'll probably put it for marks, but not a lot. Just I want you to practice these questions because you're getting that final assessment at the end of the chapter, and I want to make sure that you've had some experience doing test questions on these. So I'll weight it low. It's more for practice, but I still want you to do it. Okay, and that'll be start of tomorrow's lesson. Okay, signing out. Have a good day, everybody.